on Nova.
Major funding for NOVA is provided by the following: the David H. Koch Fund for Science, supporting NOVA and promoting public understanding of science. The Corporation for Public Broadcasting, and by contributions to your PBS station from viewers like you. Thank you. Additional funding from Roger and Vicki Sant.
In the darkness of space, there are violent forces at work. Cosmic rays shoot across the universe. Asteroids billions of years old stream towards Earth. And solar winds wreak havoc. Their destination, the edge of space. Our upper atmosphere. It's Earth's first line of defense against the hurtling space rocks that we see flare into brilliance as meteors. A protective buffer against the high-energy solar wind that creates the beautiful northern lights. And crucially, it's a key link in a global electric circuit that blankets the planet from pole to pole. Far below, the surface of the Earth is hammered by 8 million bolts of lightning every day, up to 100 strikes every second. Most lightning strikes from the clouds towards the surface of the Earth. But occasionally, the most powerful bolts are accompanied by a ghostly and fleeting flash above the clouds, reaching all the way to the very edge of space, but lasting only milliseconds. The story of these strange lights in the sky began one night in 1973, when a U.S. Air Force pilot named Ronald Williams was surprised by an unusual sight.
There was a typhoon over the South China Sea. I happened to be flying over the typhoon. And as I was going right towards the center of the typhoon, there was a big thunderstorm just off the center of the typhoon. All of a sudden, just by accident, I was watching it, because if I'd have been doing anything else, I wouldn't have saw it.
Williams saw a bolt of lightning go straight up from the top of the clouds.
When it came up, I happened to be watching it, and I just watched it go up. I reported it, and nobody had believed me. They said lightning don't go straight up. Has a discharge on something.
But it turned out that Williams was not the only pilot to see lightning emerge from the top of a cloud and shoot upward towards space. As sightings accumulated, they became a part of aviation folklore, rare and unconfirmed events that hovered just outside the boundaries of real science. Until another chance sighting provided more evidence.
A fellow by the name of Jack Winkler had some detectors out. He was looking for something else, but he discovered them by accident with equipment that was operated on dark nights in Minnesota.
While testing a low-light video camera in 1989, Jack Winkler and a team at the University of Minnesota accidentally captured a black and white image that seemed to show the elusive upward lightning the pilots had described. Fittingly, this ethereal phenomenon became known as a sprite, a whimsical name that captures its fleeting nature. These giant pillars of light sparked an intensified interest in lightning and the dangers it presents to spacecraft during launch or landing.
Scientists have long understood what happens in the clouds when lightning bolts appear, but have never been able to precisely explain how lightning is created until now. A new study published Monday in the Journal of Geophysical Research appears to have solved this mystery using math. It details the powerful chain reaction that occurs in the atmosphere to spark the creation of a lightning bolt. Victor Pascoe is joining us now. He's the professor in the Department of Electrical Engineering at Penn State University, and he led this study. Victor, thank you for being here. How exactly did you and your team figure this out?
Yeah, thank you for this opportunity. We discovered this, we believe for the first time, this powerful chain reaction which leads to lightning initiation. It combines cosmic rays, so we believe that cosmic rays initiate this reaction, and also involves very high energy photons and electrons. And what is really fascinating about this mechanism which we published is that initiation occurs on a very short time scale. So if you think it takes only 1/1,000,000th of a second for lightning to initiate. And the way it works like a domino effect. So you can think about high energy domino when you really just touch it, and then it develops in a very powerful electron avalanche leading to lightning.
So tell me then, how should all of us Earthlings be interpreting this study? What should this mean to us?
Yeah, so I think that this study really provides additional insight on physics and situation in our everyday environment on Earth's planet. And we believe that we are able to uncover some really interesting phenomenology related to lightning. For example, Professor Nikolai Ostgaard and his team recently conducted research using a high-altitude NASA R2O airplane to get very close to lightning discharge. And what they discovered is that lightning appears to be producing, this lightning initiation region produces a lot of gamma rays and X-rays. But these regions at the same time appear to be optically dark and also radio silent. So all of us know that lightning usually associated with optical flash and radio noise. So our modeling actually allows to explain these peculiar features of lightning. So also, while we worked on this research, a lot of interesting ideas appeared which are going beyond lightning research.
Like what?
So this photoelectric effect, which we studied, we believe can be applicable also in relatively small volumes, and may lead to some new interesting ideas in plasma science and engineering in research which is in fields which are different from lightning. For example, we're thinking that in small volumes, this powerful domino effect can lead to X-ray emissions, and potentially we can produce new X-ray sources in the future.
Well, it's amazing that it takes 1/1,000,000th of a second, and so much research goes into it. Professor Pascoe, thank you so much for your time today.
One of the challenges with forecasting severe weather and trying to warn for severe weather is predicting those hazards accurately. One of those hazards is hail, and it's very, very difficult to study hail. It moves quickly, it breaks everything it hits, and all of our observations are post-impact. And that can be a problem when you're finding stones that look like this. This is a replica hailstone, but it's clearly been melted. It's got finger grooves that aren't natural. It's rounded on the bottom. And that's because this object modified itself by the time we were able to find it in the field. So we really need a way to observe that in free fall before it has a chance to do anything, which will improve our ability to forecast for it and warn for it in real time. Most people want to know the difference between small hail that's water coated or something like this getting ready to hit your house. And that's why we built the truck behind us, which is a camera-based system that shoots 4K footage at 330 frames a second. And the idea is to capture these stones in complete free fall on their way down before they have a chance to melt or modify. Now, in order to do that, we need a lot of light, because the camera is being exposed for a fraction of a second. So the combined output from the LEDs in this array is about 30% brighter than the sun standing on the surface of the Earth. So you actually need eclipse glasses to stand directly behind it and look at it. It is very, very bright, but it allows us to capture those images of hail in free fall. One of the challenges with building a system like this is making sure that we know that the data is accurate, that we can trust the results. Sizing is easy, right? We can throw things like a baseball or a softball even. We know exactly how big these are, and I can just chuck them through the back of the imager and see what comes out and make sure that that size is accurate. The challenge was velocity, trying to get an object that's moving at a comparable speed to a hailstone, 80, 90, 100 miles an hour. But that's why we partnered with OU Athletics. With the help of the softball team and the baseball team, those pitchers are able to throw these objects that we know how big they are through the volume at very fast speeds. Baseball was about 94 miles an hour, softball was about 55 to 60 miles an hour. And knowing that and watching the objects go through, we can calculate the velocity using the camera system and find out that it matches what it should have been, which gives us a lot of confidence in the data that we're collecting to know that those results in the field are accurate and representative of what it actually was. After building all of this system, we had to get it out in the field and collect observations. So we've actually been taking it out a few times over the course of the last year. But this spring, we've really dialed that system in. We've had it out and gotten some incredible data collection opportunities. One of those deployments, we were able to watch almost 3-inch diameter stones falling in super slow motion on the way to the ground, watching that impact with the bed of the truck and how it shatters or doesn't. Different stones behave differently. Some are rotating aggressively. Some are melting off water and shedding that as they fall through the environment. Some aren't. And this is all occurring in the same physical space. So for the first time, we're actually seeing results from this system that are challenging some of the ways that we're going to look at hail going forward. Understanding what it looks like on radar creates more accurate, more timely warnings that can help protect life and property if you're in the path of one of these storms. In the US alone, hailstorms can rack up billions of damage every year. And that's a really big, important factor for insurance companies, building a resilient community that can handle these types of events. Those are all aspects that are going to come out of this research for years to come.
Downbursts are intense, damaging winds that rush down from a thunderstorm and spread out at the ground. They're especially tough to predict in small, short-lived storms common in the southeast US and southern plains. Here at NOAA's National Severe Storms Lab, we're studying a new radar-based feature that could give forecasters a heads up before a downburst hits. It highlights pockets of cold, heavy air inside storms. When that air sinks quickly, it can unleash powerful winds at the surface. By combining this radar clue with environmental data like moisture and temperature, forecasters can better predict where and how strong a downburst might be. It's not a replacement for existing tools, but it could help forecasters focus on the right storms at the right time and ultimately provide earlier warnings. Visit nssl.noaa.gov to learn more.
Have you ever heard of phased array radar? Maybe you've seen it in the new movie Twisters. NSSL has been the world's leading developer of weather radar technology for more than 60 years, and we're currently hard at work on the next generation. Phased array radar offers meteorologists faster radar updates, better resolution and detail, and a more accurate picture of what's happening in a storm. While not in operation yet, and not small enough to fit inside a car, phased array has the potential to push severe weather forecasting and warnings forward, ultimately with the goal of protecting property and saving lives. Visit NOAA.gov to learn more about this cutting-edge technology.
Currently, there is a forecast information gap between watches and warnings.
Within this storm, here's an area of strong winds on the north side.
When a watch is issued by the Storm Prediction Center and when a warning is issued by the National Weather Service, there are no models operationally that are providing frequently updating information in that time zone. And so there's a very strong dependency on observations.
And it's a period where there's a relatively minimum of information flow, and customers and partners may be looking for information about how the storm threat is evolving in their local specific area, hour by hour or minute by minute.
There's certain groups, like people who live in mobile homes or schools or hospitals, that may need, 2 hours lead time or 3 hours lead time on the potential for hazardous weather. So being able to communicate the timing and the potential hazards to these vulnerable populations is critical, because they have to make their decisions before the warning is issued.
And what Warn On Forecast is providing is information to fill that gap. It is a system that runs every half hour, producing 3 to 6 hour forecasts, taking in the most recent observations from weather radar, from satellite, from surface data, in order to provide updated forecasts that can be looked at during that time frame to help forecasters focus in on the corridors where storms could have the biggest impact.
Warn On Forecast began as an idea because warnings are typically issued based on radar or spotter reports, and that may only give you 10 or 15 minutes of advance notice. So the Warn On Forecast was the idea that we can issue a warning based on a forecast from a weather model.
In the last 10 years, Warn On Forecast has gone from a system under development to a system that was ready to be tested. And an important aspect of that, especially since 2017, has been putting that experimental system in front of forecasters.
The National Weather Service in Norman has been on the front lines in the development of the Warn On Forecast system, where we were in the beginning back in 2017, where we had scientists from NSSL here embedded into operations and able to provide real-time feedback to the scientists on how we could utilize this. And the scientists also provided us feedback in real time, and we were able to actually craft messages such as watch to warning graphics or NWS chat posts to our partners and to the public, using that two-way communication between us and the scientists.
And because of all of those interactions, we're now looking at possible transition of Warn On Forecast to operations, and that work has also been recognized by a gold medal. It really speaks, I think, to the importance of the work that we're doing, the innovation of the science that we're doing, and the capabilities that we are developing to be used to make forecasts better.
Now we can provide a continuous stream of information between that watch to warning for people who need a larger amount of lead time.
We've seen that with tornadoes, where emergency managers have used information from Warn On Forecast to open shelters at maybe an earlier time than they would have, or staff their EOC earlier than they might have done. We've seen it with outdoor events and things where you have large groups of people, and we're seeing more and more of these stories where it really is helping them make those pre-event decisions.
I believe the future of the Warn On Forecast system is continued development where I think it'll be assimilated into operations all across the National Weather Service, because our director of the Weather Service, Ken Graham, says we're scientific first responders. So having systems like Warn on Forecast will allow us to be better scientists and better communicators of hazardous weather in that short-term 0 to 6 hour period.